In previous videos, I've talked about the derivative, the basic definition of the derivative, and done some examples giving you a way of seeing how to carry out the differentiation process with the definition of the derivative. And then I did another video that has some basic properties and basic differentiation rules, so we could kind of get started on just derivatives of very elementary functions. I also did a video that is on the product rule and quotient rule. So if you're differentiating a function that's the product of two functions, how to apply the product rule to it. And if you're differentiating a function that's the quotient of two functions, how you find that derivative. All of those videos are linked in the description of this video. Now, what I'd like to do in this video specifically is look at how do you differentiate a function that is actually a composite of two functions. So what if you have a function of another function? How do you go ahead and take that derivative? Well, differentiating a composite function actually requires something called the chain rule, and that is the focus of this video. Now, to get started with it, we need to review the derivatives that we already have in place so that when we're at a particular part of the differentiation using the chain rule, we are able to quickly come up with the derivatives of the functions that are involved with the chain rule as we go. So what I've written on the board behind me then is a set of those basic derivatives that we should already have gotten a little bit comfortable with, but I've written it up as a reminder. I suggest to my students, and I suggest to you as well, that you have a dedicated page of your derivative rules and you add to it as you go through the learning process about derivatives so that they're nicely, concisely in one place and you're able to then compare and contrast different functions' derivatives. So let's take a look. So as a review, the derivative with respect to x of a constant is just 0. The derivative with respect to x of x is 1. The derivative with respect to x of x to the n power, where n is a rational number, is bring down the exponent n, keep the base of x, and subtract 1 from the exponent. The derivative with respect to x of e to the x is itself. So the derivative of e to the x is e to the x. The derivative with respect to x of sine x is cosine x. The derivative with respect to cosine x is negative sine x. The derivative with respect to x of tangent x is secant squared x. The derivative with respect to x of cotangent x is negative cosecant squared x. The derivative with respect to x of secant x is secant x tangent x. The derivative with respect to x of cosecant x is negative cosecant x cotangent x. And then we have our properties. If I'm taking the derivative with respect to x of a constant times a function, it's the constant times the derivative of the function. And remember that tick on the name of the function tells me it's the derivative. The derivative with respect to x of two functions that are added or subtracted is the addition or subtraction of the two derivatives. But here's where we start to get where we have to be much more careful. When we look at the derivative with respect to x of a function f of x times another function g of x, it is not the multiplication of the derivatives. That is not a thing. If you try to do it that way, you won't get the right answer. What you have to do when you're differentiating a multiplication of two functions is take the first function times the derivative of the second plus the derivative of the first function times the second. Now, this is plus in between, and I know adding two terms, addition is commutative, so really that could be written out in either order, just as long as in each of the terms you have one of the factors being the function and the other factor being the derivative of the other function, and that they each get their turn in being differentiated. Next up is the derivative of a quotient of two functions. Now the derivative of a quotient of two functions, if you watched the earlier video of the differentiating with the product rule or the quotient rule, we talk about the function in the numerator of the fraction being the function that's high, and the function in the denominator of the fraction being the function that's low. And we kind of have a little phrase that's a catchy phrase to help us remember. It goes low d high minus high d low over low low. So that denominator squared. Now this one you have to be careful about keeping track of which one's first because it's a minus in between. And we know that subtraction is not commutative. So low d high minus high d low over low low. Now these are all the review of the ones that were in earlier videos that I've posted. And this video specifically is talking about what about trying to take the derivative of a function of another function. So the derivative of f composed with g of x. How do you do that? Well, if you've got y equals some function in u, and that's a differentiable function of u, and u, that's in this parentheses that is running through f, is a differentiable function in x, then I have my function y equal f of g of x, which is just another notation for f composed with g of x is f of g of x. That is a differentiable function of x, and if I look at the differential notation with dy over dx, I can do that with dy du, that expression that links the two together, and multiply that by du dx. Now another way of writing this out, which is the way that I always think of it, is the derivative with respect to x of f of g of x. So the function that's this outside is considered the outside function, and the function that's been run through the x's of that outside function is considered your inside function. So when you're differentiating a composite of functions, thinking of it with this notation, you take the derivative of the outside function, leave the inside function alone, and then multiply by the derivative of the inside function. Now I'm going to erase the board and give us some examples of the composite function, but I'm also going to look at derivatives of products of things and quotients of things as well to keep reminding us of that, and also help us determine, well, which type of function do I have, so how am I going to decide which rule to apply? And some functions actually have a lot of this stuff going on in different parts of it. So you have to think, well, what's the appropriate rule to use at the stage of the differentiation I'm doing on this function that's more involved. And one more thing before I go to those examples is that there's a key element in this that you need to work on and make sure that you have really strong in your thought process. And that is the difference between when two functions are multiplied and when there's an outside function acting on the inside function. So making sure that I can identify when I have the product of two functions in which I need to use the product rule to differentiate it, or whether I have a composite of two functions, in which case I need to use the chain rule to differentiate it, is huge in this context. So make sure that you also keep looking at those and being very discerning on which case you have. Let's go to some examples. So to start, I'm going to work with these two examples. The first one is f of x is equal to cosine of x squared. Now, a lot of times these parentheses will be around the argument that cosine is acting on. And when I see that, I have where normally we would have cosine of just x, but here I have cosine of x squared, cosine of the function x squared. So I have a composite function here. And going back to what I was saying about a lot of times you'll see these parentheses, there'll be also times where it'll just write it as f of x equal the cosine of x squared. So both of those ways of writing it do mean the same thing. Now, is this a product or is this a composite function? Is this an action on my value of the x squared? Well, it's an action on it. The cosine is acting on the argument of x squared. So this is a composite function. It needs to be differentiated using the chain rule. Now, to apply the chain rule to this, I need to identify which one's the outside function and which one's the inside function. Sometimes I'll have you practice looking at how you rewrite the two functions that would be composed to end up with this expression. And to end up with this, our inside function would be x squared, and it will be plugged in to the placeholder that the cosine is acting on. That's one way to look at it. Another thing you can kind of think through in a lot of situations, and it proves beneficial, is what would you do if you plugged a value in for x in your order of operations? Because when we're plugging our value for x in order of operations, we really work from the inside out, and we're supposed to differentiate from the outside in. So that kind of helps us. So if I put a value in for the x, first I would square it, and then I would take the cosine of it. So the cosine is the outside action in this one, and the x squared is the inside function. So for this derivative, our f prime of x is take the derivative of cosine of an angle, and the derivative of cosine of an angle is negative sine the angle. So I write negative sine of x squared. And then I need to, by the chain rule, multiply that by the derivative of the inside stuff. And the derivative of x squared is 2x. Now, when I want to rewrite this so that I can write the expression in the way that it would be least likely to be misunderstood, negative sine of x squared multiplied to 2x is better written as, well, negative times positive is a negative, and then we'll write this 2x sine x squared. Okay, let's look at the next one. Here, this is f of x is equal to cosine squared x. That's not the same thing as what we just did. In fact, when you look back at where this notation of cosine squared x comes from and what it means, remember that was just an agreed upon way of writing the function f of x being the cosine of x quantity squared. They mean the same thing. So if I were to take a value of x and put it in for our x here, we would take the cosine of that number and then we would square it. That's your order of operations. And your order of operations works from like your inside out with nested parentheses, but our differentiation differentiates from outside in when I'm differentiating a composite function and I need to use the chain rule. So this derivative f prime of x, my outside action here is a variable to a number power, a variable expression, trig function acting on our variable. So since I have a number power here, I'm going to bring down the exponent, keep the base the way it is, subtract 1 from the exponent, but then because of the chain rule, I need to multiply by the derivative of the inside stuff. And the derivative of cosine x is negative sine x. So I'm going to multiply by negative sine x. And when I do the simplification, this is 2 times cosine x. I don't need to put the 1 power on it anymore. And then times negative sine x. So that'll be negative 2 cosine x sine x. So notice, completely different functions, and I did get unique derivatives for those two different functions. Let's look at some more examples. With this next example, I have f of x is equal to the tangent of 5x cubed plus 2x. And I'm asked to find the derivative of that. So my tangent of that, that's an action, that's a composite function. So I need to use the chain rule. Now think if we plugged a value in for x, we would need to carry it through this polynomial to get a value out, and then we would take the tangent of that angle. So my outside action is the last thing that applied to order of operations. So the tangent function here is the outside action, and that 5x cubed plus 2x is the inside. So when we take the derivative, we have to look at the derivative of the tangent, keep this inside thing the way it is. Well, the derivative of tangent of an angle is secant squared that angle. So I'm going to write secant squared that original 5x cubed plus 2x. And then I multiply that by the derivative of the inside function. So the derivative of 5x cubed plus 2x, well, that's more than one term, so I need to keep parentheses around it. So that's going to give me 15x squared plus 2. Now rewriting it, my f prime of x, I will have the 15x squared plus 2 times secant squared of 5x cubed plus 2x for our derivative. Now this next example has a few things going on. We're going to put a little bit more into it. So this function f of x is x squared cosine x plus secant x squared. So overall, I have two different terms. So I can use that property of derivatives that I can take term by term differentiation. So I can differentiate this first term and then add that to the derivative of the second term. However, also what's going on is I've got a product rule, a product of two variable expressions in my first term. So when I'm differentiating that first term, I'm going to need to use the product rule. In the second term, I have the secant acting on x squared. So that's a composite function in the second term. When I'm differentiating the second term, I'm going to need to use the chain rule. So let's get started. So my f of prime of x, so just focusing right now on this x squared cosine x's derivative, the product is between x squared and cosine x. So it's the first function x squared times the derivative of the second function, derivative of cosine x is negative sine x, plus the derivative of the first function, so that's 2x, times the second function cosine x, and then that's plus the derivative of secant of x squared. Well, that's the derivative of the outside function, leave the inside stuff alone, and then multiply by the derivative of the inside stuff. Well, the derivative of secant of an angle is secant that angle tangent that angle. And my angle's x squared. So that's going to be secant x squared tangent x squared. And then finally, times the derivative of the inside stuff, the derivative of x squared is 2x. So this derivative, f prime of x, is negative x squared sine x plus 2x cosine x plus 2x times secant x squared tangent x squared for our derivative of that function. Let's look at some more examples. F of x is equal to e to the 5x. So remember, with the exponential function, it's e to the variable power of x here would be e to a power's derivative is e to the power. But then I need to multiply by the derivative of the power when it's number based to letter expression in the exponent, and my base is e. So the derivative of 5x is 5. So this derivative comes out to be 5e to the 5x. Just also, since we're right here with this and just did that one, if I have a function f of x is equal to e to the negative x, then to differentiate that, f prime of x is going to be derivative of e to power is e to power, so e to the negative x, but then I have to multiply by the derivative of the exponent, and the derivative of negative x is negative 1. So that derivative, f prime of x, would be negative e to the negative x. This second one in this series of functions we're differentiating actually has more than one layer of the chain rule. And when you have more than one layer, I remember my professor in college explaining this as, well, it's like an onion. You have to peel it from the outside in the layers. And I didn't quite get like his analogy then, but it's one that I go back to because it makes a lot of sense. When we think about our nested parentheses for our order of operations, we plug it in the innermost and then the next and then the next. So those are the layers of the onion. But when we differentiate from the outside function in. So if I rewrite this first, this is that sine of 4x squared plus 1 to the power 3. That's what that tucked exponent means. So now, I think about, I would plug a value in for x and get this angle. Then I would take the sine of that, and then I would raise that to the third power. But when I differentiate, I have to go outside in. So the first thing I need to do in differentiating it, so this is f prime of x, is a number power on an expression that has a letter in it. We're going to bring down the exponent, keep the base the way it is, subtract 1 from the exponent, and then at that stage we're supposed to multiply by the derivative of the inside stuff, right? But the intermediate inside stuff is sine acting on an angle. Well, the derivative of sine acting on an angle is cosine acting on that angle. And now I'm finally at that times the derivative of the innermost stuff. And the derivative of 4x squared plus 1 is 8x. So when I rewrite this, notice there's a multiplication here, and here, and here for the different layers of the chain rule. So when I think about rewriting, I'm going to tuck that exponent of 2 in the notation that we agree upon meaning the same thing. And this factor of 8x, we're going to multiply to this 3, and 8 times 3 is 24. So my f prime of x is equal to 24x, multiplying those guys, and then times sine squared of 4x squared plus 1 times the cosine of 4x squared plus 1. That, I will admit, is probably the trickiest one of the video, just because of the several different layers that we have that we apply the chain rule. Now our last one from this segment is f of x equal cosecant of 5x cubed plus 4x, and again we want to find the derivative for it. So when I think about, if I plugged in an x, I'd get this angle, and then I take the cosecant of that angle. So then I differentiate from the outside in. So I'm going to differentiate the cosecant of an angle first, leave the angle the way it is, and then multiply by the derivative of the angle. So my f prime of x is, well, the derivative of cosecant an angle is negative cosecant that angle cotangent that angle. And then I want to multiply by the derivative of the inside function, and the derivative of this inside function is 15x squared plus 4. So then my derivative f prime of x is negative, parentheses around that 15x squared plus 4. You need to have those parentheses because it's more than one term. And if you don't put the parentheses around it, it means something different. So then we have our cosecant of that 5x cubed plus 4x, and then cotangent of that 5x cubed plus 4x. Now, one thing I want to bring to your attention, and I know it surprises students when they're first learning to differentiate, is that for some reason they have it in the back of their head that the differentiation process makes it get smaller. And I admit that if you do a lot of derivatives of polynomials to start with, especially if you do like the first derivative, then the second derivative, then the third derivative, you kind of have that thought kind of placed in your mind that you think that's going to happen all the time just because it happened with polynomials. But that's not the case. We can start off with a very calm looking function, and its derivative is an expression, a function that is a much longer function in writing it out than the original is. So sometimes I liken this to those little like sponge toy things that are, you put them in water and they blow up into a specific shape or whatever. These derivatives can get big even for some pretty calm, small functions. Well, hopefully these examples have been helpful, and I'm going to keep posting other videos if you want to see more examples, and just like the video if it's been helpful, and also subscribe to my channel if you'd like to be notified for when I post new videos on calculus topics, statistics topics, and algebra topics in general.